Hi guys, this is Kamran Siddiq here and welcome to the tutorial lecture for the ideal vapor compression refrigeration cycle. In this lecture we will be having a brief overview about this refrigeration cycle, and at the end we will solve an example to get a better idea about this refrigeration cycle. Okay, since we know that Carnot cycle is the most efficient cycle that is operating between two different temperatures. However, it has two major drawbacks. Number one, the compression process involves a liquid vapor mixture which requires a compressor that will handle two phases, and this is not feasible at all. Number two, it involves expansion of high moisture content refrigerant in the turbine. Okay, so the ideal vapor compression refrigeration cycles, it actually solves the issues which are encountered in the Carnot cycle. It is a feasible cycle as well as ideal that can be modeled to solve, that can be modeled on which the actual cycles can be designed. Okay, unlike in the reversed Carnot cycle, the refrigerant here is vaporized completely before it is compressed and the turbine is replaced with throttling device. Okay, so we can see here down with our TS diagram of this process. Here the compression process is taking place in the vapor phase. So that means it doesn't involve the problem of of compression at in two different states. So this it is a feasible process. And secondly, the turbine here is replaced with the throttling device. So in throttling device there is no issue whether the refrigerant is in highly moisture content or not. It won't be an issue. So this is resolved by the ideal vapor compression refrigeration cycles. So the major processes involved in this cycle are isentropic compression in a compressor, number 2, constant pressure heat rejection in a condenser, number 3, throttling in an expansion device, number 4, constant pressure heat absorption in an evaporator. So that means in the first process we have constant entropy. Number second, we have a constant pressure. Number 3, since a throttling is happening in an expansion device, that means the specific heat per kg will remain constant. So H here in this case will remain constant in the third and fourth state. And in the end, from 4 to 1, we have a constant pressure process as well. Okay, so the area between this TS diagram, it represents the heat transfer for an internally reversible process. Alright, so we move on here. The ideal vapor compression refrigeration cycle involves an irreversible throttling process to make it a more realistic model for the actual systems. Well, like I mentioned before here, throttling process, we don't have any issues with the moisture content of the refrigerant. So this makes it a more feasible yet an ideal model on which the actual models can be designed or modeled. Okay, here are the few equations. The COP, coefficient of performance, for a refrigerator is given by QL over work net. Since COP is the ratio between the input over output, so in the case of refrigerator we have the input which is QL, that is the heat absorbed by the refrigerator from the surrounding, and for the case of a heat pump the input is QH, which is the heat that is absorbed by the environment from the heat pump. Okay, so this was a brief overview. Now we'll move on to the example. So there you go. So the example statement is a refrigerator uses a refrigerant 134A as the working fluid and operates on an ideal vapor compression refrigeration cycle between 0.14 and 0.8 MPa pressures. If the mass flow rate of the refrigerant is 0.05 kg per second, Determine number A, the rate of heat removal from the refrigerated space and the power input to the compressor. Number B, the rate of heat rejection to the environment. And number C, the coefficient of performance of the refrigerator. Okay, so looking at the diagram here, we know pressure here in this case in the state 4 and 1, which is 0.14, and the second pressure given is 0.8 MPa, which is happening between state 2 and state 3. Okay, first of all, now in order to determine the work and heat transfers, we need to find the value of specific heat at all these 4 points. We'll begin with point 1 and then moving on with the given data and the the solved input, the solved outputs. We're going to find the successive values of the specific heats. So first of all, we'll start with the state 1. In the state 1, we see, we'll just put it right there. Okay, so at the state 1 we have pressure 1 that is equal to 0.14 MPa. Okay, so now we have the pressure and we have to determine H. So it's pretty straightforward, since at state 1 we know that the refrigerant is in the saturated vapor form, so we have two inputs. To mention here, in order to solve these value from the property tables, we need to have at least two input. In this case, we know the pressure and we know the saturated vapor stage here at 0.1. So we open the property table here. So we have opened the saturated refrigerant table, which is table A11, and we'll see the corresponding values. So the pressure is 140 kPa. Here is between these two values, and we have to find Hg. So this is it. It's the value between these two. So I'll just write the direct values, will not go into the interpolation. Well, if you don't know or you're unaware about the interpolation, I'll make a separate video about interpolation, and you can learn from that as well. So we'll get Hg, and we'll also need Sg, which is between these two values. So noting it down, we have H1 equals 239.19 kilojoule per kg, and S1 is equal to 0.94467 kilojoule per kg. Alright, so moving on for the state 2. So what do we have here? Number 1, we have the pressure value, which is 0.8 MPa. And since we mentioned that 1 to 2 process is isentropic compression, so that means the value of entropy S here remains constant. So we may write here that we have P2 equal to 0.8 MPa and S2, which is equal to S1, which is equal to 0.94467 kilojoules per kg. Okay, so using these two input, we'll go to the property table. Alright, so another thing here, that since in this case we have a superheated vapor state, so we'll go to the superheated vapor table. This is saturated refrigerant, superheated, yeah, here we go. So the pressure is 0.8 MPa. We will go to 0.8 MPa pressure. Here it is, and the value of S is yeah, it's round about here between these two values. So by interpolation we'll get H2 equal to 275.4 kilojoule per kg. Okay, I beg your pardon here. I guess the unit for enthalpy is kilojoule per kg Kelvin. So we can write it here. Sorry for the inconvenience. There you go. So now we have H1 and H2 values. So now we'll move on to state 3. What do we know here? Here we know that we have P3. Let me do that. P3 that is equal to 0.8 MPa, and we have a saturated liquid state. So that's pretty easy as well. So we'll go to the property table. Sorry, so we have 0.8. 0.8 is 800 kPa, which is here between these two values. So corresponding value of HF between these two is approximately 95.48 by interpolation. So H3 is 95.48 kilojoule per kg. Next up, at state 4. At state 4, since as I said earlier that in the throttling process we have a constant specific heat value, so that means H4 is equal to H3, which is equal to 95.48 kilojoule per kg. So there you go. Now we have all the values of specific heats, and now we can use them and put them simply in the formula for heat transfer and work input to find the required values. So I'll just bold them up for our convenience. Okay, so now in the A part we were required to find the rate of heat removal from the refrigerant space and the power input. So heat removal is QH. So Q, since it's a rate of heat transfer, so it's Q dot. There's a trick here in MS Word to write Q dot. You write this code and you press Alt X. There you go. This is pretty easy and faster. So Q dot we know that is equal to M dot into beg your pardon, QH is H3 minus H2. So QH here is H2 minus H3 minus H3. Alright, so putting values, since the given value of mass flow rate is 0.05, so 0.05 into 275.4 minus 95.48, 5.48 is equal to 9 kilowatt. There you go. So next up we have to find work input. So work input, we'll write it as work input, which is equal to m dot into h2 minus h1. So this is equal to 0.05 into 275.4 minus 239.19, which is equal to 1.81 kilowatt. So as expected, the work input is pretty low compared to the heat which is rejected out of the refrigeration cycle. Okay, so now we've got these two values. So in the second part we have to find the rate of heat rejection to the environment, which is, oh, beg your pardon, here I guess we made a slight mistake here. In the part A we were required to find the rate of heat removal from the refrigerated space, that is QL. Remember that, keep that in mind, that the rate of heat removal from the refrigerated space is actually QL and the heat rejection to the environment is QH. Alright, so we were required to find QL in part A. I remove that to remove this confusion, but remember that in part A we were required to find QL. So we'll write it now. QL is equal to m dot into, now QL is actually H2 minus H4. Since heat is adding, so we'll subtract H1 from H4, which is H1 minus H4. 0.05 into H1. H1 is 239.19 minus 95.48. H4, which is equal to 7.19 kilowatt. So now in the last part we are required to find the coefficient of performance. So since we talked earlier that coefficient of performance of a refrigerator is equal to QL divided by WN. So putting the values of QL and WN, we have 7.19 divided by 1.81, which is equal to, we'll need a calculator here. So 7.19 divided by 1.81 is 3.97. Thank you very much. It's 3.97, the coefficient of performance, which is approximately equal to 4. So this is it. So 4. So this means that this refrigerator actually produces the output 4 times the input provided to the refrigerator, which is talking practically, it is very good compared to the coefficient of performances of the actual refrigeration cycle. So this is the ideal coefficient of performance for this particular conditions. And if we had the actual cycle in which we would have lost these entropy in 1 to 2 process, and we would have lost our pressures in the stage 2 to 3 and 4 to 1, this value of coefficient of performance would have dropped quite significantly. Okay, so that's it. Thank you so much, guys, for attending the lecture. I hope it helped. If you have any requests, if you want me to make any request about a specific lecture, you can drop it in the comments. I hope you enjoyed today's lecture. Thank you so much for attending once again, and bye bye. Take care.